In this video, we're just going to recap the idea of redox titrations and run through an example so we can ensure that the same principles are applied when you do the calculations. Now, I'm going to use the most common example of a redox titration that you see in an exam, which is the one between manganese or manganate. So, the manganate ion is pink, okay? And if you titrate this in acidic conditions with a reducing agent, such as iron 2+, I'm going to balance that by putting that as a 5 there, then you get manganese 2+ ions, water, and iron 3+. Okay, so this equation should really be ingrained in your mind, right? This is pink, so when this reacts, that pink colour disappears. So the way you know the titration is finished is when there's no longer, or this pink colour no longer disappears, or there's like a persistent light pink in the solution. So in this we have manganate, so this is the oxidizing agent, and this iron is the reducing agent. Okay, so in a redox titration we tend to react them so that we can get equal quantities of both. And that is the purpose of a titration. You try to find out when equal quantities have reacted. And if you know when equal quantities have reacted, then you can work backwards to calculate the concentration of an unknown substance. It's similar to an acid-base titration, and there you use equal quantities of acid, equal quantities of base. When it's neutral, that's the end point. You look for the indicator to be neutral at the end point. Here, we've got equal quantities of oxidizing agent reacting with equal quantities of reducing agent, and when the oxidizing agent no longer reacts, that's when you know it's the end. So there's no longer any reducing agent in the solution, and that means that equal quantities have been added. Okay, so let's say for argument's sake that we had 20 centimetres cubed aliquot. So that's what you're taking out of a unknown concentration of iron 2+ solution. Okay, so you've got an unknown concentration of an iron 2+ solution, and you've got 1 decimetre cubed of it. So you've got 1 decimetre cubed of an iron solution of unknown concentration, iron 2. And you're taking 20 centimetres cubed of that to react. Okay, and let's say that reacted with, for argument's sake, 14.1 centimetres cubed of 0.01 MnO4- solution. So this figure here is the average you would get in your titration. So you take 20 centimetres of the solution, you do your titration, it's 14.1, then 14.1. Okay, so that's where this figure comes from. Alright, so what we're going to do next is work out how many moles of MnO4 have reacted. Okay, and to do that, we do the volume in decimetres cubed, so 14.1 over 1,000, times that by the concentration, 0.01, and that would be 1.41 times 10 to the -5. So that's the number of moles of MnO4- that reacted. Okay, now that's interesting, but we want to find the number of moles of iron. And if you look at the balanced equation, you'll see that 1 mole of manganate reacts with 5 moles of iron. So if 1.41 times 10 to the -5 moles of manganate have reacted, 5 times as many moles of iron must have been originally present. And this is a key step. So you've got to factor in this 1 to 5 ratio. This is something that is not often present in acid-base titrations. So to do that, we times it by 5. So 1.41 times 10 to the -5 times by 5. Okay, and that is 7.05 times 10 to the -4. So that's the number of moles of iron 2 that were present in our 20 centimetres cubed aliquot. Okay. But when we're looking for a concentration, as what we're looking for here, we don't quote it in moles per 20 centimetres cubed, we quote it in moles per decimetre cubed. So we now need to convert this into moles per decimetre cubed. So we do 7.05 times 10 to the minus 4, and we times it by 50. Now the reason we times it by 50 is because we took a 20 centimetre cubed aliquot. That is a 50th of a decimetre cubed. Okay? So we've got a 1/50th of a decimetre cubed, we need a whole decimetre cubed. Okay? So we times it by 50. Alternatively, for the ease of maths, okay, we can times it by 1000 over 20. If you like, that's still 50. Okay? 1000 being 1000 centimetres cubed in a decimetre cubed, 20 being the volume that you took. Okay? Now if you do this, you will get a figure of 0.03525 moles per dm cubed, or 0.035. Okay, so this is a very quick summary of the redox titration process. Just use the same thing, the same process for all the redox titrations you do. Remember to focus in, or to factor in, I should say, the ratio here. It may not be 1 to 5, it may be 2 to 5 if it's a different substance, it may be 1 to 3, whatever it is, that needs to be factored in to ensure that you get the correct value.